this is one of them disassembled. And when and if you do use those, be sure that the U-bolt part of it is bearing against the dead end part of the cable, not against the working portion of the cable. Because when you tighten those things up, the U-bolt will tend to crimp the cable and would tend to weaken the working portion of the cable. So put the U-bolt on the dead end part of it where it goes around the turnbuckle, goes around the thimble. Here's a picture of one done that way. Well, again, this is very underexposed. I wish I had taken more care with this one. But anyway, here's a piece of cable. Here's a cable clip, and again with the U-bolt against the dead end here, which is sticking out here. Usually we'll use 3 of those, and here is the thimble and the turnbuckle, and that is fastened too. Now here is a really big tower. This is probably the heaviest base insulated tower ever built. This was in Romslow, Germany at VLF station. This tower is 1,148 feet high, 7 feet in diameter, has an elevator going up inside the tower.
Every ham should have that.
Every ham should have one of these. Sitting on a base insulator, and you can see the size of the base insulators compared to those 2 guys standing alongside it, and they're no midgets. However, I wanted to point out that, again, they follow the same principle of a ball and socket connection between the base of the tower and the insulator. Again, so that any movement of the tower does not put bending moments on the base insulator. The load on that base insulator is 500 tons, and that is a lot of weight.
Where is their spark?
Right here. There's one end of it, and the other end is off here. They would arc from the corona ring down to that, and this is the braided ring in the center of the 2 insulator segments, and the arc from here down here. Now those are pretty wide gaps on that. The reason that they're pretty wide gaps is that this is on a 1,000,000-watt VLF radio station, and there's about 250,000 volts of RF voltage across this thing in operation. So, of course, the gap has to be pretty wide. If lightning strikes it, it'll go over that gap. But the tuning network that's in a big building right next to the tower is, of course, insulated for high voltage in the first place. And so a lightning surge isn't going to hurt that. It'll still go over the gap. Now, here's a picture of an excavation for a hand self-supporting tower. This is a tri-ore tower, one of these extendable towers. Shows the rebar in place. This hole is 7 feet deep and about 4.5 feet across. This was all made up now in preparation for the pouring of the concrete. This is also the Tristeo tower with the concrete foundation and the tower in place. I laid this umbrella down on top of that foundation just for scale. You can see the size of that.
The official Whit icon.
Yeah, that's right. It's the official measure. 1 meter or something, whatever it is. Now here's a diagram of this particular foundation that you just saw. The reason that it's bailed out at the bottom is that in this case you could not follow the manufacturer's recommended 7-foot depth, because in making a test boring we discovered there was hard rock at 4 feet down. And we managed to dig into the upper part of that rock. It was somewhat disintegrated, got down to about 5 feet. That's as far as we could go with that. Well, since we could not follow the manufacturer's recommendations, again we had to go to some design. And this undercut has a particular meaning because, again, under the EIA specifications, you may calculate, if you have an undercut toe that way, you may calculate and add the weight of the soil in a 30-degree cone from that up to the surface, and say that that is adding to the moment of restraint of the foundation. And the soil is calculated at 100 pounds per cubic foot. So in the calculation, we use this amount right here, calculated a 30-degree cone up there, how much soil was in that, and added that to the upset moment of the upset moment of restraint of this foundation. This foundation has 4.53 cubic yards of concrete, which is 122.3 cubic feet, and it weighs 18,345 pounds. You probably can't read this thing, and I won't even try to go through it for you, but this is a calculation of the moment of restraint on this particular foundation. Comes out with the total moment of restraint, both from the upset moment of it, that is, if it was sitting out on the ground. The moment due to the lateral bearing of the soil is 50,500 pounds. The moment of restraint just from the upset moment is 55,035 foot-pounds. And the total and the moment from the uplift on the winter side of that cone of earth is 49,007.5. So we have a total moment of restraint of 155,260 foot-pounds on that particular foundation, which is at the NT5 station. So that is about a 3-to-1 safety factor on that one. Here is a detail of the foot of that Tristão tower, which is extendable up to 72 feet and carries a substantial antenna load on the top. I want you to look at the way the tower leg is connected into the tower base plate, which itself is fastened into the concrete foundation. The connection to the foundation is made by what are called standard concrete hooks. These are 1-inch diameter. They go 3 feet down into the concrete and have a hook on the end of it that locks it into the concrete. There's 2 of them at each leg of the tower, 1-inch diameter. They fasten to this plate, which goes up alongside a plate that's welded onto the tower, and there are 6 3/4-inch screws here. Here is a place where they are in shear stress. There's an uplift on the underside of this tower of approximately 22,000 pounds, and that's distributed along 6 of these screws, which are 3/4-inch diameter, have a cross-section area of maybe, 6/10 of a square inch. It comes out that the shear stress on each bolt is about 4,000 pounds per square inch, which is quite safe for the structural steel. This is a picture of the NT5B Tristão Tower, largely compressed here. It extends much higher than that, but Jim usually keeps it down at about that level. Right here is the base of the tower and the motor drive mechanism that raises the motor to the tower. And that is the end of my talk, fellows. We have a few minutes if you would like to ask any questions before we disband. Yes, thank you.
Is it possible to buy that last 6-foot section you showed that went down to the base of the extension of your power wire? You have a physically white section you mentioned here from the power company.
Yeah, the power company uses those things for insulating down guys. Yeah, you go find the power company scrapyard. Insulators because they have very low capacity, so they can't insulating the power for the purpose of using the power at the same time. I like to keep that capacity out of that.
Is that steel inside here? What's physically inside the power?
That's right.
Fiber. Well, the reason I ask is I use Philly strand, and I like to have the last 10 feet coming to the guy section with steel because of the protection against grain fire.
Yes, that's right. See, that's an organic. It's very bad practice to use those coming on down to the ankle. Get a brush fire or weeds and melt that stuff in the ground country down. Yes, sir.
Would you mention something about the dynamics of, say, wind gusting or stuff like that, like a thunderstorm coming up?
Yes, for very tall guys, you consider what we call the dust factor in the tower, the formulas in the EMA standard 3.2. Yeah. Now, this amateur radio club maintains a connection with that standard. It's available for study by engineers, and I do caution you that it is an engineering document that takes substantial study to see exactly what they're saying. The information is there. And the dust factor is certainly significant on towers that are quite tall. For amateur towers in general, I would say that it's negative. Consider the dust factor. That is response to sudden dust that will make it go distant. Power towers, I mean, there's the broadcast stations and the like, where you have towers upwards of 300 feet. It certainly is a definite factor that has to be considered. Any more questions? Yes, sir.
The rule of thumb about the tension on different guy wires. I didn't quite understand that. You got 3 guy wires, 4 guy wires, all the same tension, or what kind of rule of thumb?
I would take great attention on the code. If you have a multiple set of guy wires, it is profitable to start considering the tower as several sections and consider the wind loading on each section as being resolved on its own set of guy wires. On really tall towers, so you need a lot of sections, not a lot of levels of guys, right? That is the way to go about it. I just showed an approximate solution for 2 guys. It's rare that hands need to go much more than that. Yes.
Have you written the book? Is this information available for future reference?
Not on this particular
No
subject.
handouts?
I wrote a textbook some years ago that was published in 1962 entitled Radio Electronic Transmission Fundamentals, treats with the generation and handling of high power radio frequency energy. The book is out of print and find it once in a while. But it doesn't say anything about this tower.
What would you go by, or is there a rule of thumb? Would you buy, what is it, steel or galvanized iron, guide wires, that new polyplastic fiberglass stuff?
Well, I prefer to go ahead and use steel myself. It's works very well and much less expensive than to go with the organic guide cables. They are quite expensive to put the infittings on. Yeah. That's the problem with Philly strand and use organic.
Philly strand's
Whit.
going to just straight guy clamps now.
Quit.
Yeah. That's about that.
3 minutes.
Okay, we got to get out of here because there's another
Thank
group of people coming in. Thank you.